Alright, 2012 AMC problem. This is problem 14 from AMC12A and problem 18 from AMC10A. And it's going to be hopefully a lot quicker than the last problem. The closed curve in the figure is made up of 9 congruent circular arcs, each of length 2 pi over 3, where each of the centers is corresponding each of the centers of the corresponding circles is among the vertices of a regular hexagon of side 2. What is the area enclosed by the curve? Okay, so first thing, what I see here is this regular hexagon. We're going to use this. This is going to make our job a lot easier. A lot easier. Regular six-sided figure. And we know that any angle in here of a regular hexagon is going to be 120 degrees. So that means that this arc is 1/3 of the circle. Okay? So we can figure out the radius of a circle, so we're going to use these to find the radii, and then we can use that to find the area. So we know that the arc length, so we have 120 degrees, 120 degrees, 120 degrees. We know that 1/3 of 2 pi times the radius is equal to 2 pi over 3. So we have 2 pi over 3r equals 2 pi over 3. Divide both sides by 2 pi over 3, and we get r equals 1. That's wonderful. Pun not intended. Okay, so what we have now is this. We have all of these arcs of side length 1. We also have this hexagon, and I know that this measure here is 2. In addition, what I'm going to do is this, okay? This area will fill in this right here. This area will fill in here because they are congruent arcs. The sectors will be congruent as well, so the areas will fill in nicely. And that's one piece, and these 3 remaining sectors, each of which they're congruent, they have a central angle of 120 apiece, so these 3 can combine to make one circle with radius 1. And so basically I need to find the area of a regular hexagon with side length 2 and the area of a circle with radius 1. So let's say area of a circle with radius 1 is of course pi r squared, which is pi. Okay, well, I see this is the only choice of pi, so I could probably go with e, but let's make sure we have it right. Okay, so let's start looking at this circle. What color would be, or sorry, the circle, this hexagon. And we know, if you don't remember the formula for hexagons, we have a formula, but I'll just work my way through it. This hexagon, hold on, I forgot to do a little bit of scribbling on here. Okay, that looks a whole lot better, doesn't it? So, this hexagon is actually made up, since it's a regular hexagon, of 6 equilateral triangles. So this area of the hexagon is going to be 6 times my area for an equilateral triangle, and we know that this apothem, this distance from the center of the edge to the circle, is 2 root 3 over 2, which is just root 3 because of a 30, 60, 90 right triangle right here. So it's 6 times times the area of each of these triangles, which is 1/2 times 2 root 3, so 1/2 base times height. 1/2 times 2 is 1, so I get 6 root 3. And my overall area for this entire figure then is both of these add together, so A of C plus A of H, which is going to equal pi plus 6 root 3, and it is e.